Hello everyone. Last time we went through part 1 of section 14.6 directional derivatives. So we finished off with an example where we had to first find the unit vector and then find our partials and use our formula for the directional derivative. And so now let's extend the concept a little bit. There's a little note at the top of the next page that sometimes the vector that defines the unit vector is not always given explicitly. Like in the last two examples, the first example the unit vector was given, and then second example a vector was given and we had to find the unit vector. But here's a situation where we're just going to have to use the given information to first find that unit vector. So it says find the directional derivative, this function at this point, and then in the direction of the unit vector that makes an angle of theta equals pi over 3 counterclockwise with the positive x-axis. So probably recommend a little sketch here of what that unit vector looks like. So it's making an angle of pi over 3 with the positive x-axis. And so that angle pi over 3 is 60 degrees. And so if you consider the angle being 60 degrees, then here's our unit vector u. This would be u1, and this would be u2, and just make a right triangle out of that, and then we could determine that the sine of 60 degrees is, well, opposite 60 is radical 3, hypotenuse 2, and adjacent is 1. So let's do the cosine first. u1 is actually the cosine of 60 degrees, which would be adjacent 1 over hypotenuse 2, and u2 is the sine of 60 degrees, or opposite radical 3 over our hypotenuse of 2. So therefore the unit vector u is going to be u1i, so 1/2 I plus u2j. So plus square root of 3 over 2 times j. So that's the unit vector we need to use. And we're going to find, so maybe we'll go so far as to say that here. The unit vector is equaling 1/2 I plus radical 3 over 2 times j. Okay, and then we're going to need some partials. So the partial derivatives are, okay, this is function of x and y, so with respect to x, y is a constant, so we'd have formula for e to the u, so e to the xy, but then times the derivative of the power. We're differentiating with respect to x, so y is a constant, derivative of x is 1, so y tags along, so y e to the xy, and then similarly for f sub y, again the formula for e to the u, so e to the xy, but now the derivative of xy with respect to y, where x is held as a constant, would be x. So x e to the xy. And now those partials evaluated at the point, -2, 0, would be x is -2, y is 0. So this is just going to be 0, because e to whatever times 0 is going to be 0. So then f sub y is going to be, okay, x is negative 2, e to the negative 2 times 0. Negative 2 times 0 is 0, e to the 0 is 1, times negative 2 would give us negative 2. So now the formula, directional derivative at the point negative 2 of f at the point negative 2, 0 in the direction of u is going to be f sub x evaluated at negative 2, 0 times u1 plus f sub y at negative 2, 0 times u2. And this u represents u1i plus u2j. So now we just substitute. So we get 0 times u1, just to be formal here, 1/2, and then plus negative 2 times u2 with radical 3 over 2. So it looks like that just crunches down to be negative radical 3. Okay, so now we get to what we refer to as the gradient. And the gradient of f, we use this upside down triangle symbol. That upside down triangle symbol, let's put it up here. This is del or nabla. So we'll read it as del, but you could read, you'll hear people say nabla as well. So if you want to read it as del, or essentially you should say gradient, I suppose. So the gradient of the function f of xy, this is going to be, the gradient's going to turn out to be a function, and then we can evaluate the gradient at a point, and we'll see in a moment what happens. But the gradient's just going to be the partial of f times I, and then the partial of y times j, and extending that to 3 variables, x, y, and z. And then if we evaluate the gradient at a point, and we dot it with the unit vector, then that's going to give us our directional derivative. So that's pretty significant. And a figure is similar to the figure we had before. If we consider some surface, this was the x, y, and z. Consider some surface. Let's say this is f of x, y. Which is our surface. Pick a point in the xy plane, x0, y0. If we project that onto the surface, then if you draw some unit vector, okay, imagine this is a line like we did before that's going to cut through this surface. So that might be something that looks like this. And then essentially what we're finding is now the del of f, or the gradient of f, is basically going to be that tangent line. So this slope of the tangent line is going to be in the direction, so this slope of the tangent is going to be our directional derivative, which is the gradient of the function dotted with u. Now the reason why this is true, let's say I wrote here reason for A, is because if you consider what del, or the gradient of f of x, y is, f of x sub 0, y sub 0, and we dot it with u, that would be, by definition, we have f sub x, let me just leave out the functional notation, I plus f sub y, j, dotted with the unit vector u1i plus u2j. Try to separate this so you know that's coming from my picture there. But then recall unit vectors, or remember, the dot product. Just take the respective I components, multiply together, respective j's, respective k's if they're in there. But see, this gives us fx times u1, and then plus fy times u2. And that is, if we look back, our definition for the directional derivative of f in the direction of u. So this just makes it a little bit easier. This formula makes it a little bit easier, and the gradient's used more exclusively than the directional derivative. Directional derivative is kind of in the background when we think about the gradient, more so than we do the directional derivative. This formula is very useful in finding the directional derivative at a point. Okay, so the example, first thing is to find the unit vector. So the unit vector, remember, is whatever the vector is divided by its magnitude. So here we have 2i plus j minus 2k divided by the magnitude recalls the square root of the sum of the squares. So square root of 2 squared plus 1 squared plus a negative 2 squared. So that's 2i plus j minus 2k over square root of 9. So that comes out pretty. So that's just simply 3. So then 2/3 I plus 1/3 j minus 2/3 k. Alright, so there's our unit vector. And so we'll need some partial derivatives. And it's in terms of x, y, and z, so 3 of them. F sub x would be, okay, y and z are constants, so that's going to be 2x times y for the first term. And then it looks like zeros for the rest of them. F sub y is going to be, now y and z are held, x and z are held as constants. Derivative of y is 1, so for the first term we get x squared. Grand derivative of y is 1, so for the second term we get minus z cubed. But then since z is a constant, the derivative of z is 0. And then for f sub z, we have the derivative, so now x and y are constants, so the derivative of x squared y is 0. Here the negative y tags along as a constant, derivative of z cubed, 3z squared, so minus 3y z squared, and then derivative of z plus 1. Okay, so then we evaluate those derivatives at the given point. So f sub x at the point 1, negative 2, 0 is 2 times 1 times negative 2, which is negative 4. F sub y at the point 1, negative 2, 0 is 1 squared minus 0 cubed, so that's 1. And then f sub z at the point 1, negative 2, 0, negative 3 times y is negative 2. Z is 0 squared plus 1, so we just get 1 out of that. And so, therefore, we could say that the gradient of this function at the point negative 1, 2, 0 is going to be negative 4i plus 1j, or just simply plus j plus k, plus 1k, or just simply plus k. So that's our gradient by the definition. Once again, just the function, the partials evaluated times the I, j's, and k's respectively. So then if we want the directional derivative of the function at this point, that's just going to be the gradient of the function at that point dotted with our unit vector. So that's the gradient of f, which, let's substitute that in here. So we've got negative 4i plus j plus k dotted with the unit vector was 2/3 I plus 1/3 k minus 2/3 k, and so that gives us negative 4 times 2/3, negative 8/3, plus 1 times 1/3, 1/3, and then plus 1 times negative 2/3, or negative 2/3. So it looks like that crunches down to be negative 9/3, or negative 3. Okay, so let's see. I guess we'll stop right there. We're at the 18-minute mark, and there's some other practice. Hopefully we can finish this section within one more part. And so that was part 2 for section 14.6, directional derivatives. And so we'll come back and firm up some more examples of the gradient, and hopefully finish part 3 in this lesson.